Hey everyone, and a massive warm welcome to the channel. It's truly fantastic to have you joining us today. Before we dive into something truly mind-bending about the universe we live in, I want to take a moment to send you all the very best wishes. Wherever you are right now, whatever you're doing, I genuinely hope you're feeling strong, healthy, and in good spirits. May good health and positive energy surround you always. Okay, let's get into one of the most fascinating and downright weird truths about light itself. You experience light every single day. It's the warm sunshine on your face, the glow from your screen right now, the colors of a rainbow after a storm. It feels so familiar, so fundamental. But underneath that everyday experience lies one of the deepest and most surprising secrets of physics. Light doesn't play by just one set of rules. It behaves like two completely different things depending on how you look at it, or more accurately, depending on the experiment you do. Sometimes light acts exactly like a smooth, continuous wave, spreading out and interacting with itself. Other times, it acts like a tiny, bullet-like particle, zipping through space and hitting things with pinpoint accuracy. This isn't just a cool trick, it's a fundamental property of light and energy at the smallest scales, and it completely changed our understanding of reality. We call this mind-bending concept the wave-particle duality of light. To understand why this is so strange and revolutionary, we need to go back in time a bit. For centuries, scientists argued fiercely about what light actually is. On one side, you had brilliant thinkers like Sir Isaac Newton. Newton, based on observations like light traveling in straight lines, think of sunbeams coming through a window and bouncing off mirrors' reflection, proposed that light must be made up of incredibly tiny, fast-moving particles. He called these particles corpuscles. This particle model seemed to explain those behaviors pretty well. Imagine throwing tiny, super-fast marbles. They would travel in straight lines and bounce predictably off surfaces. So, for a long time, the particle theory held sway. But then other observations started causing problems for the simple particle idea. Think about what happens when light passes through a narrow slit or around the edge of an object. Instead of just making a sharp shadow like tiny marbles would, light spreads out. It bends around corners slightly. This bending is called diffraction. Also, think about when two beams of light cross paths. Under the right conditions, like passing through two closely spaced slits, they don't just pass through each other like streams of particles might. Instead, they create a pattern on a screen behind them, a pattern of bright and dark bands. This is called interference. Bright bands happen where the peaks of the waves from both slits line up and add together, constructive interference. Dark bands happen where the peak from one wave lines up with the trough from the other, canceling each other out, destructive interference. This interference pattern is the absolute hallmark of wave behavior. Think of water waves. When ripples from two pebbles dropped in a pond meet, they interfere, creating areas of bigger waves and areas of calm. So, scientists like Christian Huygens champion the wave theory of light, arguing that light must be some kind of wave traveling through an invisible medium they called the luminiferous ether. For a while, it seemed like the wave theory had won the day. It beautifully explained interference, diffraction, and other phenomena like polarization, where light waves vibrate in specific directions. The discovery that light was actually a form of electromagnetic radiation, consisting of oscillating electric and magnetic fields traveling through space, cemented the wave model. James Clerk Maxwell's equations in the 19th century described light waves perfectly. Light seemed firmly established as a wave, and the particle idea was left behind. But just when physicists thought they had light figured out, the turn of the 20th century brought a shock. An experiment studying how light interacts with metal caused a huge problem. This experiment is called the photoelectric effect. Shine light onto a metal surface and, under the right conditions, it can knock electrons right out of the metal. Scientists expected, based purely on the wave theory, that the intensity of the light, how bright it is, should determine how much energy the electrons have when they're knocked out. Brighter light means a more powerful wave, so it should give electrons a bigger kick, right? And the color, or frequency, of the light shouldn't really matter for the energy of the electrons, only how quickly they were emitted. But that's not what happened. What they actually observed was baffling. First, increasing the brightness of the light did cause more electrons to be knocked out, but crucially, it did not increase the energy of those individual electrons. The electrons came out with the same maximum energy, regardless of how bright the light was. Second, and even stranger, the energy of the knocked-out electrons depended entirely on the color, the frequency, of the light. Shine low-frequency red light, no matter how bright, and you get no electrons knocked out at all. Switch to higher frequency blue light, even if it's very dim, and electrons are knocked out, and they have significantly more energy than electrons knocked out by brighter red light. This was impossible to explain with a wave model. A wave's energy is spread out. Brighter light should mean a more energetic wave that should give electrons more energy, and the frequency shouldn't be the critical factor for the maximum electron energy. This is where Albert Einstein stepped in, building on an idea from Max Planck. In 1905, Einstein proposed a radical solution. Light energy isn't delivered as a smooth, continuous wave. Instead, it's delivered in tiny, discrete, indivisible packets. He called these packets light quanta, which we now know as photons. Each photon carries a specific amount of energy directly tied to the frequency of the light. The higher the frequency, like blue light, the more energy each photon carries. The lower the frequency, like red light, the less energy per photon. Einstein explained the photoelectric effect perfectly. An electron is knocked out only if a single photon hitting it carries enough energy to overcome the force holding the electron in the metal, called the work function. A red photon, even if there are many of them, bright red light, doesn't carry enough energy individually to knock an electron out. A blue photon does carry enough energy individually, so even a single blue photon, dim blue light, can knock an electron out. Brighter light just means more photons, so more electrons are knocked out, but each one still gets its energy from one photon, so the maximum energy depends only on the photon's energy, and thus the frequency, not the total number of photons, brightness. For this explanation, Einstein won the Nobel Prize, and the particle nature of light was firmly back on the table. Light acts like particles, photons, when interacting with matter to transfer energy. So now we have a paradox. Light clearly shows wave properties, interference, diffraction. But it also clearly shows particle properties, delivering energy in packets, photons, as seen in the photoelectric effect. How can it be both? It seems impossible for something to be both a spread-out wave and a localized particle at the same time. The answer, fundamentally, is that light is neither purely a wave nor purely a particle in the classical sense we understand from everyday objects. It's something else entirely, a quantum object whose true nature is described by quantum mechanics. The wave and particle descriptions are complementary models we use to understand different behaviors of light. When we set up an experiment to detect wave-like properties, like interference patterns, light behaves like a wave. When we set up an experiment to detect particle-like properties, like discrete impacts or energy transfers, light behaves like a stream of particles. It's as if light reveals whichever face we ask it to reveal by the way we choose to look at it. This is the essence of wave-particle duality. The most famous demonstration of this weirdness is the double-slit experiment performed with light, or even with electrons, which also show duality. Imagine a light source shining towards a barrier with two very thin, closely spaced parallel slits. Behind this barrier is a screen that detects light, like photographic film or a modern sensor. If light were purely particles like tiny bullets, you'd expect to see just two bright bands on the screen directly behind the two slits. But that's not what happens. Instead, you see a series of many bright and dark bands, an interference pattern. This is undeniable wave behavior. The light waves passing through the two slits interfere with each other constructively and destructively. Now, here's where it gets truly bizarre. What if we make the light source so incredibly dim that only one photon is emitted at a time, traveling towards the slits alone? You'd think a single particle would have to go through one slit or the other and just hit the screen behind that slit, building up two bands over time. But that's not what happens either. Even when photons are sent through the apparatus one by one, with long gaps in between so they can't possibly interfere with each other, the interference pattern still slowly builds up on the screen over time. It's as if the single photon somehow passes through both slits at once and interferes with itself like a wave. However, when we try to sneak a peek and put a detector right at one of the slits to see which slit the photon actually goes through, the interference pattern vanishes. We just get two bands. By trying to observe the particle property, which path it takes, we destroy the wave behavior, the interference. The photon seems to know how it's being observed. This experiment highlights the core mystery. Light exhibits both wave and particle characteristics, but never both simultaneously in a single experimental setup. The active measurement forces it into one behavior or the other. This wave-particle duality isn't just a quirky fact about light. It's a fundamental principle of quantum mechanics that extends to matter as well. Particles we think of as solid, like electrons, protons, and even large molecules, also exhibit wave-like properties, including diffraction and interference. Louis de Broglie proposed that all matter has a wavelength associated with it, inversely proportional to its momentum. This has been proven experimentally countless times. So, this duality is a universal feature of nature at its most fundamental level. It tells us that the classical categories of wave and particle are insufficient to describe the quantum world. Things exist in a fuzzy state of possibilities described by a wave function until a measurement is made, collapsing it into a definite state we can observe. Understanding that light is both wave and particle has been crucial for developing modern technology. The particle nature, photons, explains how solar panels work. Individual photons from sunlight knock electrons loose in the panel material, generating electricity. It explains digital camera sensors. Photons hitting pixels create electrical signals. Lasers rely on stimulating the emission of specific photons. The wave nature is essential for understanding how optical lenses focus light in cameras, telescopes, and microscopes. It explains how fiber optic cables transmit information using pulses of light that reflect internally due to wave properties. Interference is used in precision measurements, holography, and anti-reflective coatings. Without embracing this dual nature, none of these technologies would exist as we know them. So, the next time you flick on a light switch or see the colors of a sunset, remember you're interacting with one of the universe's most profound puzzles. Light isn't just waves rippling through space, nor is it simply tiny bullets flying. It's both and neither. It's a quantum entity that defies our everyday intuition, beautifully demonstrating that reality at its smallest scales is far stranger and more wonderful than we could have ever imagined before quantum mechanics came along. This duality isn't a flaw in our understanding, it's a deep truth about the fabric of our universe. It challenges us to think beyond simple categories and embrace the inherent weirdness and wonder of the cosmos we inhabit. Thanks for exploring this incredible journey into the nature of light with me today.